there are essentially only three matrices like this. There are only three, and you can prove that, right? If you impose these conditions, hermicity, traceless, then there basically you can show there are only three matrices, and these three matrices are a convenient choice of the Pauli matrices. Pauli introduces matrices to describe spin of electron in non-relativistic quantum mechanics. So sigma 1 is 0, 1, 1, 1 on the off diagonal. Sigma 2 is imaginary unit minus I and I on the off diagonal. And sigma 3 is 1 and minus 1 on the diagonal. Okay, so these are the famous Pauli matrices. So the Pauli matrices have a famous commutation relationship. Let me just use AB, sorry. Sigma A, sigma B is equal to 2I epsilon ABC sigma C. Okay, so we define the generators of SU2 So the generators of SU2 are defined to be half times the Pauli matrices, okay? If we do this, then the Lie algebra, and I will formally define what Lie algebra is today. The Lie algebra of SU2 generators is given by commutator of TA. TB is equal to I epsilon ABC T of C. Now, have you seen this algebra before somewhere?
Angular momentum.
Angular momentum. Anyone else? How many students?
Didn't we have something similar a few classes ago with the J matrices? Or something?
Exactly. Yeah. So this is the same Lie algebra as the Lie algebra SO3. Okay.
So this is why SU2 and SO3 has a relation.
Exactly. This is basically reflective of the fact that there is a homomorphism between SU2 and SO3. Okay, so basically, I will do that right now, and after doing that, I will essentially move towards a more formal description of Lie groups. Okay. But before that, are there any questions? Okay. So let's talk about the relationship between SO3 and SU2. Okay. So let's make a motivation. Let's make a comment motivated by quantum mechanics. So you don't have to understand quantum mechanics to follow what I'm going to do now, but I just want to motivate this by showing why it's relevant in physics. So physically, what happens is that when you say rotate a particle with, say, spin half in physical three-dimensional space, this operation, this operation induces a transformation on the Hilbert space of the spin half particle. The transformation or this transformation corresponding to the rotation in physical space is an SU2 transformation. Okay. So what I'm trying to say is that suppose we have a spin half particle in our lab. So there's the spin. Now, suppose that this is your reference frame. Let me use a different color. This is your reference frame. And this is the position of the particle. Now, suppose that you just rotate your reference frame or the particle. You're not doing anything. You're not poking it with stuff. You're just like rotating the whole system. And the new, position of the system is given by the blue arrow. Okay, so there is some rotation that takes you from the green arrow to the blue arrow. Okay, so correspondingly, so the particle has, its state is given by some point on a Hilbert space. So this is your Hilbert space, meaning that the space of states. And suppose this is the state vector psi. Now, as you rotate in the physical space with R, the state vector on Hilbert space will change from psi to a new vector, psi prime. And this transformation that takes you from psi to psi prime will be U, which is an SU2 matrix. Okay? So this is Hilbert space. Okay, this is the quantum mechanical motivation for studying the relationship between SO3 and SU2. Okay?
Could you explain it one more time?
Right. So suppose that we have a particle in a lab. Okay, so this is a spin half particle, like an electron. Now, suppose I rotate my system. So its position vector is given by the green arrow. Okay. Can you see the green arrow?
Yes.
I mean, some people are colorblind, so let me know if you have problem seeing the green arrow and the blue arrow. Okay. So so the green arrow is the initial position of the particle, and then you make a rotation of the particle such that it ends up in the blue arrow, the position of the blue arrow. Okay. but it's a rotation. That's what's important. And it's given by the matrix R.
So the spin direction is preserved, right, under R?
Yes. Yeah.
Okay.
Yeah. Okay. So now the idea is that, the idea is that your initial particle, the initial position was described by some wave function, some matrix wave function in your Hilbert space. So sorry, let me just use a different color. So this was the initial wave function in your Hilbert space. But after you rotated your particle, the state of the system is described by a different wave vector or state vector, which is psi prime. But this is happening in Hilbert space, the space of states, not physical space. Now, the question is, how are these two vectors related in Hilbert space? The answer is it's related by a U2, SU2 vector, SU2 transformation U. Okay.
So we won't go into the proof. We're just like accepting this as a fact to motivate what comes further.
Yeah. This is a fact from quantum mechanics. You might even call it one of the postulates of quantum mechanics. Okay. I'm just using this to motivate why we are looking for, why physicists are interested in the connection between SO3 and SU2. Okay, this will have nothing to do with the mathematics that follows, but it's a good motivation. Okay. All right. So let's let's construct the homomorphism between SO3 and SU2. So let R be a position vector in three-dimensional, say physical, Euclidean space. Okay. Now, I'm going to express R as a matrix, capital X. Okay. So the matrix capital X is going to be the dot product between R and the Pauli matrices. So what I mean by this is that it's X sigma 1 plus Y sigma 2 plus Z sigma 3. And if I write it more explicitly, then it's going to be Z minus Z along the diagonal, X minus IY on the top of diagonal, and X plus IY on the bottom diagonal. Okay, is this clear? I'm just representing R as a matrix, the position as a matrix.